Good morning. So today we are starting day 2 of kind of the introduction into physics. So one of the things we need to talk about is when we start doing all these calculations or we are doing measurements in terms of science, there's a certain degree of which we can actually estimate our measurement. So for example, if you stand on a scale is only going to go out to the 10th place. So let's say on that scale, it's going to read that your weight is 120 pounds, 0.5. That means it is only certain that you are 0.5 pounds. Now, you could be 120.5432100 pounds, but the scale has limitations and it can only measure to a certain degree. Similarly, you might be wondering, okay, well, how old is Miss Baker? Okay, so how old am I? Well, one of those things when you're trying to consider age, you know I'm definitely not in my teens, okay? You definitely know that I might be in my 20s or I might be in my 30s, all right? I'm probably not in my 40s yet. Please, hopefully you didn't say 40s. So you have a pretty good estimated range as to how old I may possibly be. Now you can be extremely precise and say that I am 27.5 years old. That's pretty precise. I mean, you even said I was 6 months old, right? So that's pretty precise. But just because something is precise does not necessarily always mean it's accurate. And for the record, not in my 30s yet. Yes. All right, so when we look at accuracy versus precision, accuracy is how close you're going to be to the true value, whereas precision is how many times can you replicate that exact measurement. So say, for example, we're doing an experiment and it calls for 25 milliliters. Okay, well, that 25 milliliters, every single time you measure it, it may be 25 milliliters or it may not be, right? It's kind of just like when you look at a recipe. And it calls for a pinch of salt. That's like the one thing that breaks my heart every time I cook. I'm like, a pinch of salt? That's not a quantitative measurement, right? That's horrible because everybody's pinch is a little bit different. So when you add that pinch of salt might be 1/8 of a teaspoon, or it might be 1/4 of a teaspoon, or it might be a whole teaspoon, depending upon how much you actually add. So when we're doing science, we want to make sure that we not only are accurate, but we're also very precise. So if we look at a measuring stick and we say, okay, a measuring stick has all these little tick marks on it, right? So here's 2 inches, here's 2.5, here's 2.25, okay? And then here would be 2.125, okay? So we can go down to a pretty accurate degree of measurement if we are using a ruler like this. However, if I still have a value that's between 2 of these lines, it's going to cause me to have to estimate. And so when I estimate, I cannot estimate past my degree of certainty. So I can't be like, okay, this is 2.743102345, right? So we would never want to give that many digits. And so when we look at significant figures for today, the more significant figures that we include, that means the more certain we are of that particular value. All right, so when we look at a balance, for example, if it goes down to the centigram versus the decigram, okay, we are looking at, are we going to the 10th place, or are we going to the 100th place, or are we going to the 1000th place, or beyond, okay? So if we can go to the 1000th place, so say we go to 0.001 on a balance, maybe we measure something out. When we go that low, that's pretty precise. Okay, so the nice thing is when we have things that give us a number and it spits back a number, we can pretty much trust that. But if you think of like a graduated cylinder, very similar to the ruler example, you actually just have those tick marks on the side and you're trying to estimate, okay, well, how many milliliters is this liquid? And it gets especially more difficult when you're looking between 2 values. Okay, so when you're trying to go between, this is going to affect our number of significant figures. Here, I can go all the way down to the thousands. That's pretty precise. Here, because I only have, say, this is 5, 6, 7, 8 milliliters, I would only be able to go one past my degree of certainty. So I know for sure that it is at least 4, but maybe it's about 4.5 milliliters. Okay, so I'm going 1 degree past my degree of certainty here. Okay, I'm not going to be able to go out to the thousandths place like my balance would. All right, so again, it's important to be very, very accurate if we are doing a lab, because a lab experiment might call for something like 36 milliliters. And each time that you repeat that experiment, you want to make sure that you are using the exact same amount. You guys remember from the beginning of the year, we talked about variables and how changing certain things can affect our outcomes. Well, it's super important. If you change the amount that you are adding each time, that's not a good thing, okay? So if you look at these two trials, the first one, 35.8, is only 0.2 milliliters off from what the true value is. The second one is 1.2 milliliters off. So trial 1 is definitely going to be a lot more accurate because it's closer to the 36 milliliters. If it calls for 15 grams, and we add 15.9, 15.9, 15.8, you see how all of those aren't by 15, right? They're all 0.9 or 0.8, but they're all around the same value. So this one would be pretty precise because it isn't necessarily close to the true value, so it wouldn't necessarily be accurate, but it is very precise because I'm measured to almost the exact value here every single time. So if I take a look at this bullseye, so you guys know obviously with a bullseye, the goal is to actually hit the very, very center, okay? Well, if we look at hitting the center, we have some in the blue that you notice are pretty accurate. They're pretty close to the true value. But do you see how they're kind of scattered all around? Okay, that means they're not very precise. Precise is being able to replicate the exact same shot, like here, over and over and over. So I was able to get the exact same shot every single time here, exact same result, but does not necessarily mean that it is to the true value, which is at the very, very center of our bullseye. So if you look at these 3 examples, this one, very, very precise, not necessarily accurate. This one, all of our values are very close together, so that'd be very precise, and they're at the very center of our bullseye, so it is also accurate. And then this last one, if you look, none of them are very close to each other, so it's not very precise. And they're also not very accurate because they're not in the center of that bullseye. So there is a link to a sig+fig video. I want to make sure that you guys watch this. This is a great introduction into sig+figs, and it's also a good reference if you're like, I'm not quite sure about sig+figs. Definitely check it out. So the reason why we use those sig+figs is because those measurements do have limitations and there are errors in it, right? So we're going to have to estimate when we're filling up that graduated cylinder to that degree of uncertainty. So when we say that the vaccine for corona is 95% effective, right? That means that it is 95% effective. It does not mean that it's 95.011102000% effective, right? So if you look on all your Clorox bottles, you'll notice that it says it reduces bacteria up to 99.99%, right? That's a pretty precise estimation that it is actually able to reduce 99.99%. So it's pretty important to make sure that we are only using one estimated digit, okay? So we can't use a decimal and go all the way out to here because that makes it almost too precise. So some of our rules for sig+figs, and you do have a handout. If you look at the start here for Tuesday, there is a handout that you want to put in Notability and kind of use that as your kind of key to help you as you start learning these sig+fig rules. Again, I've had juniors come back and tell me every year, man, I really wish I focused on sig figs my freshman year, so then I was good moving on into chemistry. Okay, so with sig figs, the non-zero digits, so that means anything 1, 2, 3, 4, 5, 6, 7, 8, 9, are always going to be significant. So if you look here, 52.3 has 3 significant figures. 4,783.62 has 1, 2, 3, 4, 5, 6 sig figs. Okay. If a 0 gets sandwiched, so the zeros are always the tricky part. Okay. So if a 0 gets sandwiched, like here, do you see how you have 3 zeros, boom, 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 between 2 non-zero numbers? Those would be counted as significant. Okay, so this one has 5 significant figures. This 0 got sandwiched between the 5 and the 9, so that's 3 significant zeros. All right, so our leading zeros are just placeholders. Okay, they're never significant. So if you look, decimal point and then 0, 0, 0, those are not significant. And the reason is because I could rewrite this as just 5 times 10 to the negative 1, 2, 3, 4th. Okay, and if I rewrote it like that, then it would only be significant because of the 5. Okay, so those leading zeros at the very, very front, these two right here, not significant. Trailing zeros are significant if there is a decimal place. So do you see how there is a decimal point here, and then it includes the 0 in the 0? That is telling me that it is certain out to the thousandths place. Okay, whereas if I write 230, if there's no decimal point there, that 0 is not significant. It's only significant for the first 2. Okay, so those trailing zeros at the very, very end are only significant if there is a decimal. Okay, no decimal, like I had mentioned that 230. If you look here, these 4 zeros, not significant. All of these zeros at the end, not significant. So if you are using scientific notation and you had something like 5.2 times 10 to the 4th, you only are going to count these 2. Okay, those would be my 2 significant values. If it is 5.0, there is a decimal there. That trailing 0 is significant. That would have 2 as well. If it was just 50 times 10 to the 4th, there would only be 1 significant digit. No decimal place here. That 0 would not be significant. Okay? This power up here, remember, just adds in zeros, and those zeros are going to be placeholders. So those exponent zeros, okay, that we're going to eventually add in once we move the decimal place, are not significant. All right, so there's a couple rules as to how we multiply and divide. Multiplying and dividing is the easy one, okay? If I am multiplying something together, like 2.05 times 2.9, 2.05 has 3 sig figs, 2.9 has 2 sig figs. So once I multiply it, I'm going to get an answer, and then I have to give my answer to the lowest number of sig figs. So since I only had 2 sig figs here, this number needs to be rounded using my regular convention of rounding, so that I only have 2 sig figs. Okay, so the 11.89 gets rounded to 12 grams. So this does not matter if you're going to multiply or divide, you follow the exact same rule. Whatever the smallest number of sig figs is what you report your answer to. I always suggest here, write down your answer, and then after you've decided how many sig figs you got, round it. Okay, just in case if you mess up your rounding, that's an easy way for me to be able to give you partial credit. Adding and subtracting is a little bit harder, but it's not impossible, okay? When you do adding and subtraction, you need to line these up, kind of like you were back in 2nd grade, where you lined up your decimal point. So if you look, my decimal point is lined up in each one of these. And then I'm going to draw a line down the least certainty. So do you see how this one's only certain to the tenths place? This one goes to the thousandths, this one goes to the hundredths, okay? That means I can only give my final answer to the tenths place, okay? So I'm going to look all the way at the decimals. So past the decimals, look at my tenths, hundredths, thousandths, and go to the lowest degree of certainty. So once I add these up, I'm still going to do the exact same addition, but do you see how I have that line cutting this off? Okay, so I know my answer is 220.4, but I still have to look just behind it and say, okay, well, would 2 round up the 4? And on this one, it wouldn't. So my final answer is just going to be 220.4. If my final answer had been 220.4, then I had a line, and it was, say, 7.2, because I look at that next number, that would round up the 0.4. So it'd be 220.5 for my final answer on that one. Okay, so when you set up our addition subtraction, it's going to be the exact same way that you would do this if you were a little kid. It's just you're going to add in that line, and again, that line is going to help us determine our degree of certainty. Again, only going to the fewest number of places after the decimal place. So the fewest number of decimal places after it. Okay? Also, don't forget, of course, we got to include our units. If units are given, we want to include that because that gives us meaning to our numbers. All right, guys, go ahead and give today a try and see how you do.